welcome back to the hellgeekarena, and today we are here to discuss about a probabilistic data structure called Bloom filter. Now Bloom filter is a data structure that has been used for membership testing, and it has been adopted as a component for a lot of highly scalable architectures. Now before moving into how Bloom filter works, let's first try to understand what is membership testing. So as far as membership testing is concerned, so the kind of problem it solves is like, let's say you have a set of objects that are coming into your plate, like let's say alpha, then beta, Charlie, delta, and so on, right? So let's say these kind of objects are coming to you, and at any point of time you might be asked a question whether an object X is present into this set or not. So one very first intuitive idea that comes to our mind is like we can store these into an array or a linked list, and kind of try to traverse it. So let's say this is an array, we are storing alpha, beta, Charlie, and so on into it. At any point of time, let's say somebody asks us whether gamma is present in this or not. So what we are going to do is that we are going to traverse this array from starting point till the end, and try to find whether gamma is present. And if gamma is present at some point, we are going to stop our iterations and we are going to return it. Otherwise we are going to say yeah, it's not present. So for this, if we are using a linked list or an array, the time complexity that we face with it is O of n, and the space complexity is also O of n, where n is the number of items that we have in it. So another way to solve this problem would be to use a hash table. So in a hash table, what happens is that the basis of a hash table is basically a hash function, which let's call it an h, which takes each of the objects as input and returns back a value from 0 to m. Now 0 to m are marked into indices of a hash table. So let's say this is 0, this is 1, this is 2, this is 3. So whenever let's say alpha comes in, we pass it to hash function. Let's say hash function returns us 2. So alpha gets stored at second position. Let's say then beta comes in, to we pass it through the hash function, and let's say the hash functions returns 3. So beta gets stored over here. And then let's say we get a question that whether gamma is present into it or not. So we again pass it through this same hash function, and we check whether gamma is present over here or not. So it's going to tell us that let's say for gamma the value is 0. So we are going to check whether whether gamma is present at 0 or not, but this is empty. So we can say that there's nothing present over here, and we are going to say that gamma is not present in our set. But in case alpha if we are asked whether alpha is present in our set or not, then we'll pass through it hx again. We are going to get back 2 from it, and then we can say yes, alpha is present over here, and we can say that yes, it is present. So in this case, if we see, the space complexity for us is still O of n, but the time complexity over here gets reduced to O of 1, because in O of 1 we can answer this question whether alpha or beta or gamma were present into our data structure or not, right? So we can solve this problem using hash table with O of 1 average time complexity and O of n space complexity. So here we see that the space complexity for both these solutions are O of n. That is, the space complexity is equivalent to the number of items that we have in the set. So and the time complexity, the hash table did it better, that is in O of 1, but array took O of n time. So let's see if we can find a data structure wherein we can reduce the space complexity. So this is when Bloom filter comes into picture. So basically Bloom filter consists of primarily two components. One is a bit array of size m. So if you see over here, it's an array where each cell represents a bit of 0 and 1. Initially all of them have been filled with 0. That is, the Bloom filter is empty. It doesn't have any item inside it. The second component that we have for a Bloom filter is basically a set of k hash functions. So what these hash functions are supposed to do is, like, whenever an input x is given to them, they are supposed to generate a number between 0 and m minus 1. Let's say if we are adding alpha to this particular Bloom filter, then and let's say there are two hash functions, h1 and h2, and let's say on adding alpha, the number generated by h1 is 1, and let's say the number generated by h2 is 4. So what we are going to do in that case is, basically at the first position, which is this one, we are going to fill 1, and at the fourth position also we are going to fill 1 over here, right? Now let's say beta comes in, and then we are like h1 generates 3 and h2 generates 8. So what we are going to do is, at the third position we are going to put 1, and at the 8th position also we are going to put 1. Now let's say again, the question that is asked to us is whether alpha is present in the set or not. So again we are going to pass it via h1 and h2, and since the input is same for h1 and h2, so output will also be the same. That is, it will again respond back with h1 will again respond back with 1, and h2 will again respond back with 4. And when we are going to check whether first and the fourth indexes are set to 1 or not in the bit array. So we check whether first index is set to 1 or not. Yes, it is set. And then we are going to check whether fourth index is set to 1 or not. Yes, it is set. So we are going to say yes, alpha is present in the set. Now let's take one more example wherein we get another element called delta, and we want to test whether delta is present into our Bloom filter or not. So we first pass it via h1, and let's say we get let's say 1 from h1, and we then pass it via h2, and let's say we get 5 from h2. So now we are again going to check whether h1 is whether 1 is set to 1 or not. So yes, index 1 is set to 1. Now we are going to check whether index 5 is set to 1 or not. We see that index 5 is not set to 1. So we can say that delta is not currently present in our Bloom filter. Now let's take a fourth example wherein we are asked to test whether let's say echo is present into our Bloom filter or not. Now when we pass echo through h1, what we get is, let's say, 3, and when we pass echo through h2, let's say we get 8. So what so we test that whether echo whether third index is set to 1 or not. Yes, it is set to 1. Now we check whether the 8th index is set to 1 or not. Yes, it is set to 1. So now what we see is that although echo wasn't present in our actual Bloom filter, but since third and 8th index was set to true because of some other elements which have been entered into Bloom filter prior to echo, because of that there is a false positive that has been reported by our Bloom filter, and echo has been said to be present in Bloom filter wrongly. So here we realize that though we are seeing an improvement in space complexity, in terms of that the space complexity which Bloom filter is taking is basically a kind of a fixed space of size m bits, and it is the time complexity which it is taking is also of constant time. But there is a catch over here, that it is sometimes gives us false positives. So we'll go into the details of how we can reduce the false positivity rate, and what are the formulas that come into picture a bit later. So let's go through the process once again. Like when we want to input any element into our Bloom filter, what we do is that we pass the object through a hash, through all the hash functions, and then whatever indexes are kind of generated by the hash functions, we set all those indexes in the bit array as 1. And then whenever we are asked to test whether a particular element is present into our Bloom filter or not, what we do is that we pass the object through the hash functions, and then all the indexes that are generated using that hash functions, we check whether those bits present at those indexes are set to 1 or not. If they are set to 1, we report that yes, the element is present in the Bloom filter, otherwise we say no. So the possible scenarios in case in while testing the elements in Bloom filters are like these two. So if let's say when we are testing whether an element is present into the Bloom filter or not, and we get all the indexes from the hash functions, and then we realize that at least one of them is not set to, let's say, 1, like one of them is set to 0, so it is kind of guaranteed that the element is not present in our Bloom filter, element is not present in our set. But in case let's say let's say all the bits are set to true, that is all the bits are set to 1, then probably the element is present in the Bloom filter. That is, we have seen the case of echo wherein Bloom filter wrongly reported that echo was present within the Bloom filter. So there is a probability of some false positives. So before we move further, let's see how we can tune the parameters of our Bloom filter to achieve the desired false positivity rate. So basically we have this website for which I have put up the URL in the description below. So this website helps us to define how we can define the number of bits and number of hash functions for our Bloom filter to achieve the expected number of items and expected false positivity rate. So basically n over here represents the number of items that are expected to be added to the filter, and p is the probability of false positivity. If we input these two things into the Bloom filter, if we input these two fields into this website, we are going to get the number of bits that are needed for our Bloom filter and number of hash functions that are needed for our Bloom filter. So basically it uses these formulas to calculate these two values. For derivation of these formulas, you can take a look at the Wikipedia link for Bloom filter, which I have put up in the description below. So here are some of the graphs for you. So basically p represents the false positivity rate, and n represents the number of expected items that you're going to add to the Bloom filter. So we can clearly see that as and when the number of items are kind of increasing, the false positivity rate is definitely going to increase, because what will happen is that as and when we are adding more and more items, more and more bits are going to get filled with 1, and then the rate of collision is going to increase, and more false positivity is going to be seen. Next graph over here is p versus m. P is again false positivity, and m is the number of bits that we have. So if we see over here, as and when we increase the initial number of bits in the predefined number of bits in the Bloom filter, we see that the false positivity rate is going to decrease, which is again true, because it's pretty much intuitive that as we increase the number of bits, the collision is going to decrease. So false positivity in turn kind of decreases. Now this third graph, which is p versus k, that is probability of false positive versus the number of hash function, is pretty interesting. As you see over here, it first decreases and then increases. Now what happens is that if you have, let's say, just one hash function, then if you are trying to put up too many elements through that hash function, we might see that for some of the elements, the hash function might be giving you back the same value to be set into the Bloom filter. And also, if we are increasing the number of hash functions by too much, let's say we have 50s and hundreds of hash functions, then it would mean that for one single element, let's say 50 or 100 bits would be set to 1. That means in this case also the collision would increase. So in case we have just one hash function, then also the collisions would be high, and in case we have very high number of hash functions, then also the collision would be pretty high. So we would need to find a pretty sweet point somewhere in between 1 and let's say 100, which is going to give us the least amount of false positivity rates. And this can be, we can get idea of this using these formulas that are present over here. So let's move further. So here we have already seen that the time and space complexity for array was linear, or let's say O of n, that is as and when more and more items are getting added to the array, the time complexity of finding out whether an item is present into that array or not was kind of linear. It was always dependent upon the number of elements that are currently present into the array. For the hash table, the space complexity was linear. That is, we were the space that was occupied by the hash table was equivalent to the number of elements that are present in that hash table. But the time complexity of finding it was constant, because all we needed to do was to pass the element via the hash function and get the position of that position of the element in the hash function and check whether the element is present there or not. Now in case of Bloom filter, both time and space complexity is O of 1. Now why is it O of 1? Is because we have a predefined number of bits in the Bloom filter. So we predefine M, we predefine K. So M is the number of bits and K is the number of hash functions. So basically the time is dependent upon the hash function, and space is dependent upon the number of bits, and both of them are predefined. They have no dependence upon how many elements we are adding to our Bloom filter. So hence we see that Bloom filter guarantees a constant time and constant space while searching an element. But again, this comes at a cost, that it has some false positives. So moving on, there are a lot of places where we have seen that Bloom filter is used in a lot of scalable architectures. So one good example of it is Cassandra, where before actually searching for an element or pulling out an element from a table, what Cassandra does is that it first checks the Bloom filter, whether each of the table has a Bloom filter associated with it, which Cassandra would first check into the Bloom filter whether that element is present in the table or not. If it is present, then only it will do the disk operation of fetching the element from the Bloom filter, from the table. Then similarly, using web crawlers also, some of the web crawlers, what they do is that before crawling a URL, they first check into the Bloom filter whether the URL has already been crawled or not. So this comes into picture in web crawlers as well. Even Bitcoin has used Bloom filters for wallet synchronization. Redis provides a data structure for Bloom filter, wherein you can within that Redis cache you can use the Bloom filter. So moving forward, like we already know what are the drawbacks of using Bloom filter. We already know that it does have a lot of false positives. There are possibilities of false positives, that is, but you can control the false positivity rate. You can tune it according to your usage and then check whether Bloom filter fits your use case or not. And then another drawback of Bloom filter is that values cannot be removed from the Bloom filter. So once an item has been added, there is no way to remove that item from the Bloom filter. So and the next and the last section that we have over here is basically these are some of the Java implementations of Bloom filter, which you can use if you are planning to use in your Java application. Like Guava is one of the best Java implementation of Bloom filter, and another one is Cassandra. Basically, as I told earlier, that Cassandra uses Bloom filter before to reduce the disk operations from pulling the elements from the table. So yeah, Cassandra also has its Bloom filter implementation. So these are some of the important implementations that we can use in Java. So thanks for watching this video, and stay tuned for more. Thanks a lot.